Hi guys, we're going to talk about bulk modulus and the speed of sound in different mediums. So, in any material, you can imagine the molecules connected by little springs. These springs get stronger the more you compact it, but also obviously a solid, right, will have stronger bonds than a liquid, and a liquid will have stronger bonds than a gas, where technically a gas doesn't really have any bonds at all. It's just the temperature that and the collisions of them bumping into each other that acts as this spring. That's a separate calculation. It ends up being the same result though, or we can sort of map it to this. So anyway, let's just imagine that all the molecules are connected by these little springs. Remember, springs have a spring constant that tells you how stiff or rigid they are, right? A stronger, rigid spring, right? Stronger bonds means there's more force if you try to push it. So if I try to displace this, right? If some input pushes this some distance A, we'll call that an amplitude A by some, again, external input, right? And the input actually makes it go back and forth, right? Some positive A and some negative A, then this spring will stretch and compress. Eventually, that will make this stretch and compress, right? Which will make this stretch and compress. This is called a compression wave, right? So a compression wave or longitudinal wave, right, is where you have some molecules closer together and then some molecules farther apart, some molecules closer together, some molecules farther apart, and the compression, right, moves forward at some velocity v, it propagates. But each individual molecule, like this one, just vibrates back and forth with some frequency. So the frequency is inputted, right, at some amplitude. Those are two separate things. So the distance is the amplitude, the rate, right? How fast or slow is the frequency. And the stiffness of the spring tells you how fast it propagates because it connects the molecules together. So if we actually do a calculation over a volume, we get a different quantity called bulk modulus. But the whole point is bulk modulus represents the strength of these bonds. It's the rigidity. So solids on average have a larger bulk modulus than liquids, have a much larger bulk modulus than gases. So let's properly define it. This is kind of the concept. If I push one end, this end will eventually vibrate, this one will eventually vibrate, this one will eventually vibrate. That's called a compression wave. This is what sound is. Sound is any compression wave moving through a medium. Yes, any. So, well, there's only one per medium. You can only do this in one way because if you wiggle one end with a compression, it moves through the medium in exactly one way. That's the speed of sound through the medium. So let's look at this a little more specifically, and then we'll get an equation for this. So cool. Say I have some, cubic meter or some general volume V, and I try to compress it equally on all sides. Well, that means I get a smaller cube, right? And some delta V where it got pushed inward. Great. Well, those springs then resisted, right? They're pushing back. So I have these little springs with each has a spring constant K is pushing back. So what's going to happen, of course, is it's going to resist. There's going to be some delta P that's going to push back. like as a net whole or bulk property, right? So there's going to be this bulk pressure that's pushing back. We call that the bulk modulus. So the bulk modulus is and it's a negative pressure gradient. So if I apply a positive pressure, it pushes back, right? It's the pressure response to compression. I hope that this makes tons of sense, that this has everything to do with how rigid it is. This is a measurement, a now quantifiable measurement of rigidity. We then have to divide by the fractional volume change or relative volume change. Look at that, delta V over V. So if you try to squeeze it by 1%, right, a certain delta P will happen. But if you try to squeeze it by 20%, you get a larger pressure coming out of it, right? Relative volume change. Another way to look at this is yes, the pressure response itself is the bulk modulus times delta V over V, and this then is the rigidity. I actually think this is a better way to look at it because this is the effect and this is the cause, right? Once again, right, we have cause and effect written in this. We're not going to use this formula, but this shows you what bulk modulus is in terms of its concept. The formula we are going to use is this, which is that the speed of sound is the bulk modulus divided by the density. And this is easy. If something is more rigid, it means the bulk modulus is larger. It means it fights back more if you try to squeeze it. Imagine like steel versus a marshmallow. Marshmallow is easier to squeeze, so it's less rigid, so it has a lower bulk modulus. So say I have steel. Well, steel therefore will have a greater propagation. If I flick it, patoom, right? It's going to have a larger, faster propagation where the molecules are connected more. But if it's more dense, which steel is more dense than a marshmallow. So you might ask, well, which wins? But those are two separate things. The rigidity is going to always win, by the way. That's going to be a thing you're going to want to know. But the density, right, actually will slow it down, right? And that makes sense, right? If there's more masses connected, or they're heavier, there's more in the way, more to move. So you can evoke the concept of Newton's second law that obviously if something has more inertia, which is mass, it has more resistance, it's heavier, or there's more of them. If there's more to move, the response, which is represented in the acceleration, right? And this obviously is the rigidity. Conceptually, this maps to the sound speed. In fact, and I'm tempted, I'm not gonna in this video, but you could derive this formula from this. This actually comes from this directly. It requires a little bit of calculus though, and it's really clever and almost doable, but I'm not going to show it. I'm just going to emphasize the concept here because I think this is enough, and I think it makes enough sense where you don't need the math derivation, right? More rigid is faster, more dense is slower. Boom. That's it. That's all you got to know. If you're interested in the math, come ask me, send me an email. I'll send you a link or I'll make a video. If enough people ask for it, I'll do it. I'll do it. It's cool. From this, you can actually derive the sound speed from this. But again, this response from Newton's second law, rigidity or force over mass inertia, right, gives you the sound speed. Cool. That's it. Hope that makes sense. Keep it simple, but know this. This is what we're learning right now. This is what we're learning. We're going to apply it. So now let's apply with some numbers. Here's what I mean. So let's make a little chart. Let's say material, bulk modulus, density, and sound speed. All right. Let's compare these materials. Diamond to steel to granite to sandstone to water, and even let's include liquid mercury. What's cool is that these are liquid. This is a metal, so is mercury. And these are rocks, but these are solids, right? So these are metals, these are solids, and I guess you could call diamond a rock technically, but it's a gemstone. It's also very unique. It's unique in that it is a carbon lattice, right, with very strong bonds, right? It's just carbon. The molecular symbol for a diamond, and I'm trying to draw in 3 dimensions here, is just carbon, right? It's just this carbon like crystal. Its bulk modulus, therefore, is one of the highest on the surface of the Earth, which is 443 gigapascals. Please, please, please remember that giga is 10 to the 9. Giga is a billion. It just prefixes are useful because we don't have to write out 9 zeros, right? Just going to write it in giga, right? Now, this formula requires pascals. The measurement of bulk modulus is a force because, as we saw over here in page 2, that it is the pressure response to compression divided by a relative volume change, which is just a percentage, right? So for a diamond, right, B of diamond is 443 gigapascals. That says if I try to squeeze it by 1%, I need 4.43 billion pascals of pressure to do so, because that's how much it will fight back. So if my relative volume change is 1%, then it's 1% of the pressure, which you can, if you plug in 0.01 here and you plug in 443 gigapascals here, you of course get 4.43 gigapascals over here. There you go. So that's how you apply that formula and make it make sense. But let's go back to our little chart. Its density is 3,500. If you plug that into the formula, you will get 11,250 meters per second, which is crazy fast. That's like 11 kilometers a second. That's crazy. All of these sound speeds are really fast, actually. The sound speed in air is 343 meters per second. That's one we're going to want to know. We're going to derive that in class separately. As we're going to see, that's dependent on the temperature of the gas as well as the molecular mass. That's what determines the bulk modulus. And of course, the mass is the mass. That's like the density, right? Steel is 160 gigapascals. Granite is 50 gigapascals. Notice that steel is a metal. Rock, right, is less, right? Metal is more rigid than rock in general, right? That's what that means. Metal's actually a lot more dense, also a lot more dense. Metal bonds are really, really tightly compact, even more so than diamond. That's 7,800 kilograms per cubic meter. Please don't forget that is the unit of density. That is a rho. Yes, Greek letter rho for density. Granite, rock, only 2,700 kilograms per cubic meter. Look how dense metal is compared to it. And look how rigid it is compared to granite. So we're going to want to compare these values. These are each, so rock, less dense and less rigid. Sandstone is like crumbling in your hand, very low rigidity, 0.7 gigapascals, and less dense, 2,200. Water is actually pretty hard to compress, 2.2 gigapascals, and we know its density is 1,000 by definition. Mercury is a liquid, so notice how it compares to steel. The other metals will have a larger rigidity because this is a liquid, right? So it's going to be less rigid than steel. It's still more rigid than water because it's a metal. So again, the metallic nature makes it more rigid than water, but its liquid nature makes it less rigid than steel. These words that I'm saying are really important. Like the meaning of these numbers is so more almost more important than plugging them into the equation. We obviously want to plug them in, but the equation doesn't mean anything if we don't know what the numbers mean. Density of mercury is crazy high. It's 13,500. So what we're going to want to do is compare these individually. Plug this in, you get 4529. This is all meters per second. 4.5 kilometers per second for steel, 4303 for granite, a small 564 because it's low rigidity and still pretty dense for sandstone. 1483 is a famous number for water. That's the speed of sound in water. And mercury is 1360.8. Yeah, I'll write it like that. Or 61 if you want to round. Great. Here's what I want to do. Let's compare diamond to steel and steel to granite. That's what I want to do right now. Conceptually, how do these numbers make sense? And please pause the video, rewind, make sure you guys can do those calculations on your own, right? Diamond to steel. Diamond was 443, steel was 160. Diamond is just approximately 4 times, right? We can get an exact number, right? 443 divided by 160. Sorry, not 4. That's not a 4. I'm not doing math properly. 3 times 160 is 480. So that's actually less than 3 times. Sorry, I'm getting my pen back. That's actually about 2.75 times as rigid. Cool. Which means it takes 2.75 times the pressure to change its volume by the same amount. Please understand that. It takes 2.57 times the pressure to change its volume by the same amount. That's what that number means. Rewind it, pause it, repeat that until you get it. Great. Diamond, though, is less dense, right? So less dense by, let's get an exact number here, right? By a fraction, yeah, that's about a half, right? I would say that's about a half. It's technically a little bit less than a half, going from 7,800 to 3,500, but good enough, right? Let's just say it's a half, right? I'm just trying to get a good idea. So which wins? Well, in this case, they both do the same thing because more rigid is faster and less dense is also faster. So it's not about which wins. They both combine to make diamond a faster because it's smaller molecules. Here's steel. It's denser, it's heavier, and it's less rigid. Normally, when something is more compact, normally more compact corresponds to more rigid. Diamond is an exception to this, so be careful. There aren't fundamental rules like that. Sure, there are rough correlations that more dense typically correlates, that's the word correlates, my little scribbles there, with more bulk modulus. Typically, but not always, not as a general like rule. So you have to be careful, right? So less rigid, more dense steel will be slower because as you vibrate one end, there's more inertia for it to propagate through and it's less rigid. Whereas diamond has this crazy carbon structure. Carbons are not that heavy compared to metal atoms, right? Metal atoms are a lot heavier than carbon atoms. So this is a lot more light. That carbon bond is just so strong. And I'll refer to your, chemistry course about atomic bonds and carbon bonds. They're like the strongest you're gonna get, right? Cool. Awesome. So we should expect this to be 11,000 something and this one to be only 4,000 something, right? And via the ratio, right, the ratio of B ratio to the velocity ratio, that's the word ratio, is the square root of the bulk modulus ratio to the density ratio. So if you took the ratio 2.75 times 2 and you square rooted it, that would be the ratio of the velocities. Kind of a clever math trick. Anyway, let's now compare steel to granite because I think this one's interesting. Steel was 160 GPa. Granite was 50. Steel, though, was crazy dense compared to the rock of granite. So this is rock versus metal versus like gemstone carbon lattice versus metal. Rocks are less dense by a factor of, I'm seeing that as about 3. Let me please make sure I'm accurate. Yeah, about a third. Let's just approximate, right? Going a third as dense. A third as dense will make it go faster, right? A third of the density will make the velocity go up by the square root of 3. Please make that ratio make tons of sense. Pause it until that makes tons of sense, right? The inverse square root of the density gives you the velocity. But we also have here a rigidity change. It's a third as rigid. Again, approximately, right? This is not exactly a third. This is not exactly a third, but this is about a third. This is about a third, right? Close enough, right? A third, the rigidity means the velocity goes down by the square root of 3. Again, pause it until that makes tons of sense. So that makes it go slower. So it's less heavy, but it's less force. Which wins? Well, they cancel each other out. So you should get almost the same speed. And did you notice that it is the same speed almost? And I think the answer was that the rigidity won out, right? It's less rigid more than it's dense because granite, let's go see those numbers again. Yep, granite was 4303 compared to the 4525, right? It's less bulk modulus and less dense this one. I don't know if you're gonna say wins, I don't know, right? This mattered more. The change in this was greater than the change in this. So the rigidity was a greater ratio change than the density. Boom. So this made it go slower. This made it go faster. Ultimately, granite is a slightly slower sound speed than steel. Water to mercury is a cool one, right? It's more dense. This is about what, 25 divided by 2.2. I mean, I was gonna say it's about 10. Really, it's about 11.3, 11.36. Which wins here? Which is a bigger ratio? Well, it's more dense, so it's slower. It's not as rigid. Ooh, right? So the rigidity almost makes up for the fact that it's low density. And notice how the sound speed is almost the same as water, but slower, right? Why? Because the density dropped more than the bulk modulus went up. Boom. We got it all right. That's it. Please make that make tons of sense. Again, this video, I meant to go fast, but you can rewind it, easily pause it, listen to the specific language that I use. The ratio comparison between the rigidity and the density is all where it's at. I'm imagining, boom, these waves going through these mediums. Now, this is cool. This is a good initial thing, but this is going to show us like if we can figure out the sound speed of something, we can figure out the nature of the material. The sound speed becomes like a fingerprint of like any material in existence, right? Because if you like wiggle one end, the material will kind of reveal itself. So me speaking reveals the nature of the air if we look at how sound moves through the air. I think that's kind of cool. Either way, I hope that made sense. See you guys later.